25 minutes into the deployment, nothing is moving. The CloudFormation console shows two resources as create in progress, not failing, not timing out, just sitting there with a spinner. You try to cancel the stack. You can't because the stack is still technically running. You refresh the page. Nothing changes. The problem wasn't slowness. The problem was that two resources were each waiting for the other one to exist before either of them could be created. The stack wasn't slow, it was deadlocked, and the reason it got there is that the team had the wrong mental model for how cloud provisioning actually works, a model that almost everyone starts with because it's intuitive and most of the time invisible in its incorrectness. Here's the model. When most engineers think about provisioning multiple resources, they think about it as a list, a sequence of things that get created, one after another. You write the template, you define the resources, and the cloud works through them, in order if it has to, in parallel if it can. The sequence matters, but it's still fundamentally a list. That model is wrong. The correct model is a graph. Here's what I mean. Take a simple application environment on AWS. You start with a VPC, then subnets, and subnets can only live inside a VPC, so the subnet depends on the VPC. There's an arrow from the subnet pointing to the VPC, then a security group that also needs a VPC, so another arrow, then an EC2 instance, which needs both a subnet and a security group before it can be placed anywhere. Two more arrows. Draw that on paper. What you have is not a list, it's a directed graph. The VPC is a root node. The subnet and security group are intermediate nodes that depend on it. The instance is a leaf node that depends on both of them. And the provisioning engine, whether that's CloudFormation, Terraform, or Pulumi, has to walk this graph in a valid order. It cannot provision the subnet before the VPC exists. It cannot provision the instance before both of its dependencies are complete. The graph determines the sequence. The template you write is just a description of the graph. This matters because graphs have properties that lists don't. And three of those properties are responsible for the majority of provisioning failures that don't produce a clean error message. The first property is depth. The deeper the graph, the longer provisioning takes, not because individual resources are slow, but because downstream resources can't start until everything above them is complete. This sounds obvious. In practice, teams that don't think in graphs will often add a dependency that adds a few seconds to one node and not realize they've just added 10 minutes to the end-to-end deployment because of where that node sits. The second property is cascade failure. If a node in the middle of the graph fails, every node below it fails too. This is why a single misconfigured VPC CIDR block can fail a 60-resource stack. The VPC is the root. Everything else is downstream. And here's what makes this painful in practice. The error messages surface on the leaf nodes, the resources furthest from the actual failure. The stack says it couldn't create the EC2 instance. The real problem is that the subnet doesn't exist because the VPC failed. If you start debugging at the error message, you're debugging the wrong thing. You need to find the root of the failure in the graph, not the node where the failure became visible. The third property, and the most dangerous, is cycles. A cycle is a loop in the graph. Resource A depends on resource B. Resource B depends on resource A. Neither can be created first, because each requires the other to already exist. The provisioning engine reaches this node, looks for its dependency, finds that the dependency is also waiting, and stops, not with an error, it just waits. That's what a deadlock looks like in a cloud deployment. The console shows create in progress. There's nothing to debug, because nothing is failing. Nothing is doing anything at all. Now let's go back to the deployment from the opening. Here's what was actually configured. The team had two tiers, an application layer and a database layer. Each had its own security group. The application security group had an inbound rule allowing traffic from the database security group by security group ID, the way AWS recommends, so that you're not hard-coding IP addresses. The database security group had an inbound rule allowing traffic from the application security group for the same reason. You can see the cycle. To create the application security group, the database security group needs to exist because the rule references its ID, and vice versa. Neither can be created first. The graph has a cycle. The deployment doesn't fail, it deadlocks. The fix is to separate what needs to exist from what can be added afterward. You create both security groups first, empty, with no inbound rules. You've broken the cycle by splitting the node into two, one node for the group's existence, one node for its rules. The rules can now reference each other because the groups they belong to already exist. The pattern generalizes. IAM roles that reference policies that reference the same roles. Load balancer listeners that reference target groups that reference the load balancer. The specific resources change every time. The graph property that creates the deadlock is always the same. Three things change when you stop thinking about provisioning as a list and start thinking about it as a graph. First, you read error messages differently. Cascade failure surfaces errors on the leaf nodes, not the root. When a deployment fails and the error says it couldn't create an EC2 instance, your first question should not be, what's wrong with this instance? It should be, which of its dependencies failed? The error message tells you where the failure became visible. The graph tells you where it actually started. Second, you design deployments differently. A single large stack with a deep, tangled dependency graph is a single point of failure. Breaking it into layers, a networking stack, a security stack, an application stack, each with explicit outputs that the next layer reads as inputs, creates smaller, shallower graphs. A failure in one layer is contained. It doesn't cascade to all the others. This is the architectural reason behind the practice of layered stacks. It's not an aesthetic choice, it's a graph property. Third, you catch cycles before they reach production. Both Terraform and CloudFormation detect circular dependencies at validation time. This is not optional if you want deployments that don't silently deadlock in production. The tools will find cycles you didn't know you had. The mental model to keep from this video is a question you ask every time you add a resource. What does this node depend on? What depends on it? And is there any path through the graph that leads back to this same node? That last question is the cycle check. If the answer is yes, you found your deadlock before it finds you. Provisioning failures that don't produce errors, deployments that hang rather than fail, are almost always graph problems. Cycles are the most common. Cascade failures from root nodes that failed silently are the second. Depth causing unexpected wait times that nobody accounted for is the third. See you in next one.